Hello class. Today we're going to talk about membrane potential and the action potential, the way by which nerves transmit signals from one place to another. Now, membrane potential is going to be potential just like you would consider in a battery, right? If you have a 12-volt battery, that's kind of indicating the push that's on those electrons. Something similar happens to your membranes of your axon. In your axonal membranes, there is the sodium-potassium pump. And if you remember from a long time ago, the very first unit, that pump per ATP will pump out of the membrane 3 sodium ions and pump into the membrane 2 potassium ions. Now, by doing this, you establish an electrochemical gradient. Let's look at that electro part first. So when we pump out 3 sodiums and pump in 2 potassiums, what are we doing to the charge of the membrane? We're taking 3 positives and pumping them out, and we're taking 2 positives and pumping them in. What is the net effect? Well, the net effect is we're outside of our membrane is going to be positively charged, and the inside of our membrane is going to become less positively charged, aka negatively charged. So that will be the impact that the sodium-potassium pump has on our membrane. And this difference of charge will be the resting potential of our membrane. So this pump will set up a resting potential across our membrane, this difference of charge.
Ms. Bell to the front foyer, please. Ms. Bell to the front foyer.
Now, what about the chemical component? Well, if we're pumping a ton of sodium outside and there's not much sodium inside, how do things want to flow? Right? If we had passive diffusion, we have a ton of sodium outside, none inside, what's going to happen if we, for example, poke a hole in that membrane? Well, the sodium is going to come rushing in, down its concentration gradient. What about the potassium? Well, through that same hole, the potassium would go rushing out because it wants to move down its concentration gradient. So you have this electrochemical gradient that will allow your neuron to quote-unquote fire, to send a signal from one point to another. Now let's look at how it sends that signal. This is effectively how. This here is the potential difference across your membrane that happens as an action potential occurs, as your membrane sends that signal. And it's measured here in millivolts, right? We're measuring voltage across your membrane. So the resting potential of your membrane is right here, negative 70 millivolts. Now, the dendrites off of your neuron, they will receive a signal from another neuron, and that signal will cause sodium channels to open up. Okay? So what's going to happen? If sodium channels open up, what's going to happen? Well, sodium's going to come rushing into the cell. And when sodium comes rushing into the cell, this is going to change the membrane potential. We have a bunch of positive rushing in. And you can see that our membrane potential shoots up. Now, this whole curve here is not due to just the sodium ion channels on your dendrites, right? What happens is that sodium that's rushing in, if it can reach this threshold point right here, negative 55 millivolts, this causes a cascade known as your action potential, right? Where you'll have these voltage-gated ion channels that will open up, allow sodium to rush in, and then that causes the threshold voltage to be reached on the next voltage-gated ion channel all the way down the neuron. So it may start at the dendrite, but if you reach that threshold value of negative 55 millivolts, this will cause a cascade where the opening of one channel will cause enough of a potential difference change of your membrane to open the next, and so on and so forth, until it reaches the end of your axon. Now, repolarization occurs once that membrane potential shoots up. So once you reach those positive millivoltages, you have these voltage-gated potassium channels that will then open. And if we open those voltage-gated potassium channels, what's going to happen? Well, we have a lot of potassium inside the cell that is now going to rush out. And this is in an effort to repolarize your membrane. So all of that potassium rushes out, and at this point, your sodium ion channels are going to close up, and you get this hyperpolarization that occurs. Your potassium channels close up, and then finally your sodium-potassium pump kicks into gear where your membrane becomes repolarized, right? We're pumping out that sodium, pumping in that potassium, and we reestablish the resting potential of our membrane, and it is now ready to fire again. Keep in mind, this is all happening extremely quickly. This time scale here is measured in milliseconds, thousandths of a second, which means your neuron can fire many, many, many times per second. Keep that in mind. So let's draw this out in a little bit more detail to help illustrate how this chain reaction can occur. So here's my super crude drawing of a neuron. Here we have the dendrites, the axon, and then the end of our axon, the axonal terminal, where that signal can be transmitted to another neuron. So let's say we have a neuron here that is innervating our dendrites, right? It has the ability here to send a signal to this dendrite. So this neuron sends a signal to our dendrite. We'll talk about what that signal is next lesson. It's neurotransmitters. And once that signal is received, that'll cause sodium ion channels in that membrane to open up. So sodium then can rush in to our neuron. Now, let's see what impact that has on our sodium-potassium voltage-gated ion channel. So I'm going to do a little bit of a zoom in here of this membrane, of our axonal membrane. So if we zoom in, so here is our membrane, right? What establishes that membrane potential? The sodium-potassium pump. And remember, right, our sodium-potassium pump is pumping out 3 sodiums for every 2 potassiums coming in. So as a result of this, right, we're pumping out more positive than we're bringing in. That's going to make our membrane outside, right? This is the outside of our axon, and this is the inside here. It's going to make the outside positive and the inside negative, right? The resting potential is negative 70 millivolts. So once that resting potential is established, the nerve cell can fire. So what does that look like? Well, it's going to look like this. So our dendrite has received a signal, sodium begins to rush in. Now, let's say that the voltage by this sodium channel here reaches the threshold value of negative 55 millivolts, right? Due to that sodium rushing in, we reach that threshold value of negative 55 millivolts. What's going to happen is this channel here is going to open up, and this is going to allow sodium to rush in. Right? It's going to allow tons of sodium to rush into our membrane. This is going to raise the membrane potential. Now, as the membrane potential increases, what's going to happen to that adjacent sodium ion channel, right? We have one a little bit further down. What's going to happen to that channel? Well, as we reach that threshold value, that channel will open up, and then we get more sodium rushing in. Well, then what's going to happen to the channel that's a little bit further down? I think you get the idea, right? We're going to reach that threshold value of -55, and it's going to open up and allow more sodium to rush in. Now, this is going to continue all the way down the axon until you reach the end, the axon terminal. Now, to reestablish membrane potential, what's going to happen is these ion channels here, these will close as the membrane potential gets very high, right? These sodium channels. And what's going to happen is your voltage-gated potassium channels will then open up. And those voltage-gated potassium channels allow potassium to rush out of the cell. So now you have positive charge rushing out of the cell, and that will reestablish your membrane potential, right? Your membrane potential will drop back down. Once your membrane potential has gone to that hyperpolarized point, the -75 millivolts, these channels will then close up, right? These channels will then close up, and now what's going to happen is your sodium-potassium pump is going to kick into gear and reestablish that electrochemical gradient, right? Because after hyperpolarization, what's happened? Well, you have a ton of sodium now inside the cell, right? And you have a ton of potassium outside the cell, so it's going to reestablish that electrochemical gradient by pumping in your 2 potassiums and pumping out your 3 sodiums per ATP and reestablish that electrochemical gradient. Now, I've left out a key ingredient here, which is myelin. Myelin, the fat that surrounds your nerves, what was its function again? Its function is to speed up nervous impulses, right? And how does it do that? Well, it does it by something called saltatory conduction. And with saltatory conduction, the nervous signal, because it is such a good insulator fat, the nervous signal jumps from node of Ranvier to node of Ranvier. So instead of this sequential nervous signal transduction down the axon, what you get is the signal jumping from node to node. And this dramatically speeds up the nervous impulse. So you get depolarization, right? Where your nervous impulse here causes depolarization of this membrane, and then that will further depolarize this membrane over here, and then this membrane over here. And instead of your signal moving like this, it moves like this, right? It moves way faster because it can jump from node to node. And without your myelin, in fact, your nervous system would not be functional. When I was about 19 years old, my youth leader when I was a child, he suffered from a very rare condition called Guillain-Barré syndrome, where effectively your nervous system attacks and destroys the myelin of your peripheral nervous system. So the nervous system that controls voluntary movements and a lot of obviously other aspects, but most notably would be voluntary movements, lost all of its myelin. He is completely paralyzed and trapped within his own body. His mind is completely fine. He's still all there. It's just that his peripheral nervous system has lost its myelin and thus its ability to function. So that's how important myelin is and how essential it is that we speed up these signals. Without it, literally it does not work.